Example 2.4.4, which is on three-phase circuit connections or configurations. A three-phase source has a voltage magnitude of 120 volts per phase. The three individual loads are connected that are 2 plus J1 ohms each to form three-phase loads. Find the current in phase A from the source if the circuit is one of the four possible circuit configurations. And as usual, we'll use phase A of the source as the reference phasor. So looking at the YY circuit diagram, what we can see is that the voltage right here is 120, and that connects directly across the capital AN terminals of the Y load. So we can just by inspection see that the voltage that is across ZY right there is 120 volts. So VAN is equal to VAN is equal to 120 at angle 0, since A is our reference. So that's the voltage across that is also 120 angle 0, just because of the circuit configuration. So if we want to know the current flowing here, that's also the current flowing here, so we just need to know what the current flowing through the load device is. So IA is going to be equal to IAN, which is VAN over ZY. So we get 120 angle 0 degrees volts divided by 2 plus J1 ohms, and we get a phase A current of 53.67 at an angle of negative 26.57 degrees. And that's probably the easiest circuit of the four to analyze. So let's come down to this. We have, again, we want to determine what IAA is, and we know that this is 120 angle 0 degrees. But what we want to know is this current here, which is a little bit different than that current there. Right. So what we're going to use is we need to figure out what the voltage across AB is. Here, capital AB, we want to know VAB right there. If we know that, we can determine what IAB is. And once we know IAB, we can use the relationships developed in the text for delta Y to figure out what IAA is. So there is some line to line and line to neutral conversions here. Okay. So the first place we need to start is we need to know that IAB is equal to VAB over Z delta right there. So we weren't directly given VAB. We can see that it's the voltage addition of VAN and VBN. Add those two together and you get that. What we prefer to do, though, is we prefer to do a line. This is a line to neutral quantity. This is a line to line quantity. So we really should do a line to neutral to line conversion. So VAB, which is again a line to line quantity, is found by the associated phase voltage, or we also call that a line to neutral voltage. And remember, we multiply it by the square root of 3 at angle 30 degrees. So that's just 120 angle 0 degrees times root 3 angle 30 degrees. So the magnitude of a line to line voltage is increased by root 3, and it leads the reference voltage by 30. So that gives us a VAB value of 207.85, angle 30 degrees volts. You may recognize that a lot of industrial utilities supply voltage at 208, and how they derive that is from two phases of a three-phase system. So that gives us VAB, which is our line-to-line voltage on phase A. We can use that to calculate a line-to-line current here, IAB. You can see that IAB is going to be VAB over Z delta, so that's 207.85 at angle 30 degrees volts, and we need to divide that by 2 plus J1 ohms. So that's going to give us a 92.95 at angle 3.43 degrees amps. So interesting that the current in that load is much higher in this configuration in the Y delta, and that's because of the voltage that the load actually sees being quite a bit higher. Now what we've solved for here is IAB. What the problem asked for was what the phase current delivered by the source is, which is that current right there. So you can see what happens is this current splits into IAB, and ICA are the two currents that contribute to IAA. So what we see there is that is again a line to phase conversion. And what you should remember from the text is that IAA is equal to IAB. It is going to be equal square root of 3 minus 30. Right? So we get IAA is equal to 92.95 at angle 3.43, root 3 angle negative 30 degrees. So that's going to give you an IAA of 161 at angle negative 26.57 degrees amps. So that's the answer to B. We'll see in later classes that the method that I used there is not the one that's typical. We have a little simpler analysis technique, but I did it this way because we really do need to understand what the difference between phase, a lot of times we call them phase quantities, also line to neutral quantities, or we call them line to line quantities. So we need to understand those terms, and so doing this math this way helps develop that. On to part C. What we're asked to determine is what IAB is here. So that is the phase voltage coming out of the AB source. That one's a little complicated because you can see IAB does not directly equal IAA, and it doesn't directly equal the current flowing through the load. So we have to do a variety of transformations here. But the overall idea is we're going to determine this current here. That allows us to determine IAA here, which allows us to determine IAB there. So we're going to have to work backwards and work three different currents for this one. So we want to find the current IAB flowing through the delta load. We can just write our Ohm's law for VAB divided by Z delta right there. And we see that we do get a little bit of a break here. That voltage source is connected directly across the delta load. So that's just 120 angle 0 degrees divided by 2 plus J1. And that's the same calculation we did up here. So we get 53.7 at angle negative 26.6. So that tells us what that current is right there. We now need to do a line to phase transformation to get the line current, and so IAA is equal to root 3 angle negative 30 times IAB. So that's that transformation. So that's root 3 angle negative 30 times 53.7 angle negative 26.6. And so you do that math, you get 93.0 amps at an angle of negative 56.6 degrees. So that's this current here. Now we need to know that current there, and we need to go the opposite way. IAB is equal to IAA over root 3 angle negative 30 degrees, because we're going from a line to a phase quantity, so we need to divide by root 3 angle negative 30. You can see all that does is undo the step we just did. So that puts us back at 53.7 at an angle of negative 26.6 degrees amps equals IAB. Okay, so that's part C. Let me find my mouse here, I lose it sometimes. Alright, the last one is that we want to determine the current flow right here, IAB. So we can see that the process that we're going to apply here is we'll have to do a line to phase transform off IAA, and the current flowing in AN is the same as IAA, so we just need to find the current flowing in that load right there. The problem is the voltage isn't directly connected across these terminals, so we have to do a voltage transformation on that one. So we know that VAN, the voltage that we want to know so that we can calculate that current right there, is going to be equal to the line-to-line voltage, this one right here, divided by the square root of 3 at angle 30 degrees. And we know that VAB is connected directly across the terminals of that voltage source right there, so that's just 120 angle 0 divided by root 3 angle 30 degrees, so that gives us a value of 69.3 at angle negative 30 degrees volts. So cleaning my little drawing up, that's this voltage right there, VAN. So now we can determine IAA, the line current, as VAN divided by the Y load, one phase of it. So let me find my numbers. So that's the 69.3 angle negative 30 degrees divided by 2 plus J1. That gives me 30.98 at an angle of negative 56.7 degrees. Running out of space there. Amps. So now I know the current flowing here, IAN, and I know that IAN has to equal IAA. So that's what I'm saying right there. So now we need to do a line to phase transformation to get IAB. And we know that the phase currents have to be smaller than the line currents, so we get, or equal to at least, IAA over square root of 3 angle negative 30 degrees. So that's 30.98 at an angle of negative 56.7 degrees over root 3 angle negative 30. and that gives you 17.9 at an angle of negative 26.7. I think I rounded improperly in the previous step. I think this wasn't supposed to be negative 56.7. I think it's supposed to be negative 56.6. Sorry about that. So anyway, IAB equals 17.9 at an angle of negative 26.6 degrees amps. Okay, that wraps it up.